Okay, so hello everyone again. I'm David Hicks, as you saw in the previous session. And today we're going to be talking about the AFLOW Prototype Encyclopedia for this session. And so this is a combination of a catalog of crystallographic prototypes accompanied with a software to actually generate these materials or these prototypes and decorate them with different elements to automatically create new materials for high throughput materials discovery. And so just a little bit of a motivation behind this particular work. So you may be familiar with some catalogs or resources in the community that provide structural prototypes. So for example, there's the Pearson's Handbook, the Strukturbericht series. Forgive my pronunciation of German. I've tried for many years to pronounce it, but hopefully I'm close. The Structure of Crystals and the American Mineralogist Crystal Structure Database. And so a lot of these resources have structural prototype information, but a lot of these are PDFs, so you can't really generate them in a high throughput fashion. And there's also some other computational hurdles as well with these resources. So for example, a lot of the prototypes referred to in these resources will refer to the structure via a compound name. So for example, rock salt might be referred to as NaCl or MgO, so it could be compound dependent, which is can be a little bit cumbersome, especially if you don't know what the common structure type for a particular compound would be, and it doesn't really tell you what the structure looks like. In addition, for the Strukturbericht designations, typically for rock salt it would be B1, but again, that doesn't really tell you what the structure itself looks like. And so part of the something that we wanted to overcome when we developed this encyclopedia was to have a good naming scheme that would tell you what the structure looks like. So that's one of the first hurdles that we wanted to overcome with respect to some other resources in the community. The other is that a lot of these resources require at least a baseline knowledge of crystallography. So we do, as per the previous session, we do know what the Wyckoff positions are in the space group. But a lot of these resources would give you a prototype just with the following information. So they would say that this prototype has space group 216, and it has this Wyckoff position, which we know that these correspond to the multiplicity, the letter designation, and the representative coordinate. But again, as a user, you would need to basically expand out this representative coordinate to create a geometry file for it, and you would basically need to expand it out with the symmetries based on that Wyckoff position. So again, it kind of prevents users from automatically generating these materials. And that's really where we wanted to overcome these challenges with the AFLOW Encyclopedia. And so we have structural prototypes built into the AFLOW software. So for example, you can generate, as we saw in some of the previous sessions, we can generate common structure prototypes such as the Heusler, anti-Heusler, half-Heusler. And the idea here is you can take these backbone structures, go to the periodic table, decorate them with different elements, and you can create or automatically create hypothetical new materials. And we currently have over 1,100 prototypes available online as well. So we have them integrated into the AFLOW software, and they're also available online for you to visualize them, find information about them, and also generate them online as well. And so this endeavor is known as the AFLOW Prototype Encyclopedia. And so we have a large catalog, as I said, of these structural prototypes. And I'm going to show you the web page in a second, but we also have a document, or basically an article, basically of 3 different volumes. And basically it provides a lot of structural information for each prototype. So we have a standard label, some of the historic labels, the Strukturbericht designation, similar compounds, some symmetry information, so the Wyckoff position space group, and then also some visualizations as well. And we've been working on this for quite a few years in collaboration with some of our collaborators, in particular Professor Mike Mell when he was at the Naval Research Laboratory. He started this endeavor and we joined together, and we've been building out the encyclopedia ever since. And so part 1 we had 288, and we've added about 300 in part 2, and part 5 was recently, it's currently being printed for publication, and we've added another 510. And so that brings us to this 1,100. And again, these are available online as well. And so one of the ideas that I mentioned, or one of the reasons why we developed this, was we wanted to have a descriptive label and method of generation for these prototypes. And so essentially what we've done here is we've come up with what we call the AFLOW prototype label. And that's shown here on the left-hand side of the PowerPoint. And so you can see it's a string separated by underscores. And so some of these fields may look familiar if you kind of look at them. So the first field is the reduced stoichiometry. And one thing I should mention is this is for the Wurtzite structure in particular. So this is the reduced stoichiometry. So it's a 1-to-1 ratio of the species. The Pearson symbol is HP4. Then the third field is the space group number. And the subsequent fields are the Wyckoff letters associated with each species. So for example, species A has Wyckoff letter B, and species B also has Wyckoff letter B. But this alone doesn't really nail down the exact geometrical structure. There are degrees of freedom that we also need to specify based on this symmetry. So for example, this is space group 186, and Wyckoff positions 2 Wyckoff letters B. And so the degrees of freedom for this particular label, there are 4. There's the lattice parameter A, so essentially the size of the cell, you could say. Then there's the C/A ratio. So again, these are related to the lattice parameters. And then the other degrees of freedom are the Z Wyckoff coordinates. So for species, or for Wyckoff letter B, the degrees of freedom are Z, and we have 2 B's, so 2 Z's. And so these are the degrees of freedom that we need to specify to basically generate a geometrical structure. And then we can generate the structure based on this label. And what's nice about this construction is that we can actually tune these degrees of freedom and slightly modify the cell. So for example, if we reduce the C/A ratio, we're squishing the cell. Or for instance, if we change some of the Z parameters, we can change the spacing between some of the atoms in this unit cell along the Z direction. And this is nice because we can change these degrees of freedom, but they don't alter the underlying symmetry. So even if you change these degrees of freedom, you're still creating a structure that's consistent with this label and thus the symmetry. And so this is a very powerful prototyping tool, because this is essentially the mechanism that we use to create these geometry files. And so it's nice because you can essentially generate an infinite number of structures for this label if you can kind of change these degrees of freedom and they're distinct enough. And so this is essentially the mechanism or the engine that we use to create the prototypes. And we'll see how we can do that via the command line. We've already seen a little flavor of this in the AFLOW plus DFT section, and I'm going to elaborate on that in some of the demonstrations. Okay, so before we get to the command line, I mentioned that all of these prototypes are available online at aflow.org/prototype encyclopedia. And for reference, I've kind of highlighted some of the key features in this PDF or the PowerPoint, but I'm going to go ahead and actually open a browser and we'll kind of navigate together. So let me go ahead and exit the presentation mode. And again, just for clarity, I'm going to pull up the PDF version. Just kind of keep this to the side. But for now, feel free to follow along with me. If you open a browser and if you go to aflow.org, you can scroll down. And as Professor Tower said when he introduced the web page, we have this these apps and docs. And here you can see the prototype encyclopedia icon here. And so if you click on that, it'll take you to the AFLOW prototype encyclopedia webpage. And again, just so it's easier to follow along, I'll put the link in the chat. All right, and so this is the main page for the prototype encyclopedia. You can see we currently have, as I said, 1,100 prototypes on this page. There's some basic search functionality that I'll highlight in a second, but you can also search the prototypes via space group, Pearson symbol, structuralische designation, chemical symbol. There's a prototype index, which is a sortable table. And then a little bit on Friday, I'll talk about this AFLOW Crystal Finder, which is a way to compare your structures to entries in the prototype encyclopedia. But for now, we'll kind of leave that for Friday. But for example, you can click on space group. And so you can basically navigate the prototypes via space group. So first we go to the different crystal classes. And then let's say we find the cubic space groups. And basically you can identify or find all of the prototypes that are organized by the space group number. So you'll notice that there's going to be maybe a couple entries per space group, depending on what the Wyckoff decorations are. So you can search by space group. And if you go back to the top, there's this bar here, or this navigation bar. So again, you can go by Pearson symbol. So for example, if you wanted to search through some of the orthorhombic structures, you can see here's the prototype that has Pearson symbol OC4, and you can kind of navigate that way. Again, there's the structuralische designation. So if you're familiar with this type of designation and what it means, so type A are typically the elements, B are, I believe, equicompositional binaries, and then you can kind of go on and see what the different labels are. So for example, you can click on this and then you can basically navigate via this symbol. Again, chemical symbols. So if you wanted to look for particular species, they're kind of alphabetized to the best of our ability. And then there's also the prototype index. So this is a large table, basically, of all of them. And basically, there's a sortable table, so you can sort the prototypes by the number of species, or the number of atoms in the unit cell, or the Pearson symbol, for instance. So sortable table, and then you can actually click on this and it'll take you to the corresponding prototype page. Or if you wanted to search, there's some basic search functionality. So perovskite. So you can see that there's a couple that have a perovskite in this search. So double perovskite, cubic perovskite, post perovskite, and then there's also the orthorhombic perovskite as well. Then you can reset the search. The other thing that I wanted to mention before we actually look at a particular prototype page is there's also some basic information about crystallographic conventions. So for example, especially in the PDF versions of the encyclopedia, we give brief introductions to the different lattice types. And so let's go ahead and click on cubic, for instance. So there's some information about the cubic crystal system, how we define the conventional cell, and basically how they relate to the different primitive cells. So again, for simple cubic, the conventional and primitive cell are the same. And then basically these are the space groups associated with this lattice type. Same with FCC, again, the relationship, BCC, etc. And we have this for all of the different crystal systems. So, and it's nice because it also tells you what the lattice vector convention is. So again, the primitive cell is not necessarily unique, as I mentioned before, but this is our definition of the, for instance, the face-centered cubic primitive structure. And again, it has this form that we've seen a couple of times already. The last two things I want to mention before we look at a prototype entry page is you can also look at the different space groups. So again, this is more about crystallography itself, not necessarily prototypes, but we have basically the different space group notations. So for Hermann Magwin, Hall, International, and Schoenflies, and some information about orientation, you can kind of refer to this kind of as a table if you're interested in what the different space group notations are. And there's also some additional references here if you're interested. And then the last thing is we also have a section on enantiomorphs. And I just wanted to highlight this as kind of an interesting concept, but if you're familiar with enantiomorphic space groups, basically they are space groups related to each other via mirror images. So for example, space group 76 and space group 78, they're related via, they're enantiomorphic pairs. So they're related via this mirror operation, or they're mirror images of one another. And the reason that we highlight this is we were trying to identify prototypes in all 230 space groups. And it turns out that some of the space groups were harder to identify prototypes for. And so we actually used this relationship to basically kind of, if we had space group 76, then we automatically had space group 78 because we could just do the mirror image of it. And structurally, they're equivalent, but it's just based on the symmetry. There's this mirror relationship between the structures. So kind of an interesting crystallographic concept here. Okay, so that's kind of the outline of the page, but actually let's go ahead and look for a particular prototype entry. So actually, if you hit the search button without typing anything, it'll take you to this search page here. So for example, you can search by space group, Pearson symbol, or name. So I'm going to search for corundum. And so this is a particular mineral, so Al2O3, and we're just going to click on this. And so for every prototype in the encyclopedia, it has its own entry page, and I'll briefly go through the outline of each page. So at the top, we have a JMO interface, so you can rotate the structure, similar to how you would on the aflow.org, each entry page on that website. There's also some ways that you can load a supercell, for instance, specify 1 by 1 by 1 supercell, which is just the cell back again. You can load a block that has a certain angstrom size. Takes a second to do that, I think. Yep, but a larger cell. You can view the conventional cell, the primitive cell, or you can superimpose both onto one another. So again, this kind of shows the relationship between the primitive and conventional cell. There's some Wigner-Seitz representations. So you can basically see the Wigner-Seitz cell in relation to the primitive cell. Again, you can rotate along certain axes. So some JMO functionality, I won't go through everything, but basically you can view the cell this way. Below this, we have some of the prototype information. So this is the common material, or the prototypical material for this prototype. So Al2O3. Let me zoom in just a bit. This is the prototype label that I mentioned. We have the Strukturisch designation, the symmetry information, and here is the corresponding prototype command. So this may look somewhat familiar from session 1. Again, it's similar to this AFLOW Proto command, but Proto, and I'll discuss that in more detail during the demonstration. But essentially, this is the label you have to specify, followed by the degrees of freedom. And essentially, this is the syntax on how you would generate the structure via the command line. There's some information about other compounds with this structure. And if they have a mineral name, we tried to provide it. There's also some comments when we were finding these structures in the literature. We tried to include any noteworthy comments. Below this, we have the primitive vectors and then the basis vectors. So the basis vectors are the atom positions with respect to the lattice or direct coordinates, and then the Cartesian coordinates, along with the Wyckoff position, and then the atom type. And what I want to highlight here again is that you'll notice that these equations are given in symbolic notation. So they're given in terms of ABC, alpha, beta, gamma, and X, Y, and Z. And again, this highlights that, again, you can change those degrees of freedom for this prototype and still keep the underlying prototype backbone structure with that label, but just slightly different degrees of freedom. So it's generalized. We include some references where we found the structure, some geometry files that you can download, but really probably one of the most important aspects of the page is the prototype generator. So I'm going to zoom out just a bit. But at the bottom of every page is kind of a user-friendly way of generating the prototype structure. So we've given you the default degrees of freedom, and then you can also the default species. And you can generate this structure via these buttons here. So again, I mentioned that AFLOW supports different geometry file formats. So you can create a vast postcard. If you click on that, you can see you get the postcard. Also, somebody asked about Quantum Espresso functionality. So this is really where we support Quantum Espresso, is through structure file manipulation. So generating these structures. And also, if you were to pass this into any of the symmetry functions that we mentioned, you can perform the symmetry analysis on any of these geometry file formats. So that's something that I didn't really highlight, but as long as AFLOW can understand the geometry file, which it can for any of these, you can do these symmetry analyses that we mentioned in session 2. There's also abinit, ycar, SIF, and then there's also elk. And the other thing I want to mention is, let's say you change the parameters. So let's say I'm going to say 4.0, and then let's go ahead and do iron instead. You can hit refresh JMO. And it looks like we may not, looks like there might be a small bug. But in general, you can add these on and refresh JMO, and it'll update the structure. It looks like there might be a bug on this page, but. So it looks like there's a question in the chat. Is the generation of the structure from the prototype, is there a control test on the atom overlap? Okay. So actually online there is control over this. So if you were to say, for instance, to change some of these degrees of freedom and the atoms got too close, I believe there'll be a warning on the page that says that the atoms are too close. It'll say that I think the threshold is maybe 1 angstrom. And so it'll still generate the structure accordingly, but it'll at least give you a warning. Via the command line, it's a little more general, and it actually won't necessarily give you an error. But if you try to do, for instance, a symmetry analysis after, you'll kind of get that information that the atom positions are relatively close, or maybe too close. So there are ways to test for that. And so, yes, there is a possibility of atom overlap, but this should be caught, especially if you're running additional analyses in AFLOW. AFLOW will detect basically the resolution of the atoms. Yep, no problem. Okay, so are there any questions about the online interface for the prototype encyclopedia? Again, each prototype has their own web page. And then if you were to click on to the encyclopedia icon, it'll take you back to the main page. Okay, so if there aren't any questions about the online interface, now I'll actually show you how you can generate this in the terminal. So let me just kind of resize the screens a little bit. Okay. All right, so I'm kind of going to have these side by side again. Okay, so before we actually start that, I'm just going to basically give you an idea of what the actual syntax is again. So to do this via the command line, to generate a geometry file, and by default the postcard, you would do AFLOW -- proto equals, then you would do the label, so the AFLOW label that we saw, and then you need to specify the degrees of freedom. So -- params equals, and then whatever the degrees of freedom are. And so these are the prototypes that we've been talking about, but you may recall from the previous session that there were some prototype labels that kind of followed a different syntax. And these are somewhat older prototypes. And basically, these are hard-coded, and they're generally enumerated. So this corresponds to a ternary, and they're just kind of enumerated. And you don't need to specify any degrees of freedom. So there are kind of two different prototype schemes. This is an older one, so you can still generate them. Basically, we're backwards compatible, but we're starting to kind of gravitate towards this labeling scheme because it's a little more descriptive about what the structure looks like, and it has more control over the structure. So it looks like there's a question in the chat. In the online interface, there's no possibility to assign species for different atom types. See, for example, this. So I think you may be referring to actually specifying the species here. So if you put the species here, it does update the geometry file here. It looks like maybe the refresh JMO, there may be a bug there. I think we were actually working on that just before. Oh no, it works here. So you'll notice that I specified a different species, and now I get MGPD, which was different than this MGNI. I see. So you're saying that this particular structure, the hexagonal laves, you were expecting there to be more than two species? Is that what you're saying? I see. Okay. So if in general, so the way that the prototype labels work is basically there's kind of a fixed number at least based on this label in particular. This is always going to be a binary. We will see actually in later sessions for the partial occupations, you can actually put more species on these sites that are essentially partially occupied. And Dr. Osis is going to be talking about that a little bit more. There may actually be a ternary form of this. I don't recall, we'd have to do a search, but there may be another way of adding more species to this, that maybe there's a ternary form that we found in the literature, so we made a label for it. But yes, for intermetallic, if you're trying to basically add more species based on this structure, another way to do this would be via the partial occupation module, and we'll see a little bit more of that on Thursday, or I think Thursday. So but yes, in general, we're kind of looking at ordered structures, and based on this label, the ordered structure is a binary. But yeah, great question. So yeah, hopefully we'll see a little bit more of that on Thursday, and it'll answer your question in a bit more detail. Okay. So just to recap this slide, so this was essentially, there's kind of two prototype schemes. There's an older one that's a little, that is still available, but we're starting to gravitate more towards this labeling scheme here, this method of generation. All right, so let's go ahead and start with some exercises or some demonstrations. So again, if you navigate to the virtual machine and the terminal, again, just to make sure we're all on the same page, if you type CD, you'll get, and hit enter, you'll get back to your home directory. And then we'll go into AFLOW exercises. Day 2. And now we are in 03 prototypes. All right, so we have a couple of examples here. And so the first thing we'll do is we'll go into subdirectory 1. So this is 1MGO. So you'll notice that we don't have any geometry files in there, and that's because we're going to create it. So basically, we're going to use the following prototype syntax. So we want to generate the magnesium oxide rock salt structure, and it has this label. And so you would type AFLOW -- Proto. So contrary to what we were doing before in session 1, we did AFLOW Proto, and that would generate the AFLOW in. But if you just want the geometry file itself, you just do Proto. So -- Proto equals, and again, this is the label. And again, if you kind of think to the symmetry of what this structure is, so this is rock salt. And again, as we saw similar to before, to decorate magnesium and oxygen on it, we would do Mg and O. And again, AFLOW prefers the species in alphabetic order. So Mg and O. And for rock salt, there's 1 degree of freedom only, and that's the lattice parameter. So we would do params equals, and the only degree of freedom is lattice parameter A, so 3.5 is what we're going to say. And if we do this, you can see we created a postcard, and it has the following form, and we see magnesium and oxygen. And again, as we saw in the online interface, you can toggle between the different geometry file formats. So if you hit up, you can either add the option to the command itself. So you could do --, aims, for instance, and it'll create the aims. Or again, you could also, just to kind of highlight the functionality, that it's not specific just to this command, but you can also do AFLOW --, aims, and it's the same functionality. So you can do VASP, you can also do SIF, --, SIF, quantum espresso, and then --, ELK for ELK, for instance. And so basically all the supported geometry file formats shown here, and basically these are the options that you would add to the command. Okay, so that was just to generate the geometry file. And so there are a few things that we can control further. So the first thing that you might be thinking is, so there's a question in the chat, is VASP format always the default? The answer is yes. Yes, we always do the VASP as default. And that's just because AFLOW is catered to VASP, so that's kind of our standard or our convention. So, but again, with these options, you can toggle between the two. Yep, no problem. The other thing that might be useful is, let me hit up one more time. Depending on your version of VASP, I believe you should be able to do this via the command line. So if you're familiar with the difference between VASP 4 and VASP 5 format, there's a slight difference. You'll notice that if you, in VASP 5, they want the species here. So just above the number of each type, they have the species here. So again, if you do --, VASP 5, then you can add this line here. And so this may be useful in some of the exercises in the future sessions. So that's just why I wanted to highlight that here. Okay, so the next exercise is, you may be wondering, okay, so AFLOW prefers things to be in alphabetical order, the species. So, but what if we wanted to actually change where the species are decorated? And you can do this with the site decoration control functionality. So again, cat the README, again, this information's there. So at least for the AFLOW, for the rock salt structure, we'll do that one first. So if you do AFLOW --, Proto equals ABCF8 225 AB. And so the default would be AB, but if we want to swap the species, we would do BA. And then again, we keep alphabetic order, so MG and O. Params equals 3.5. So in comparison to the default AB decoration, magnesium is on the origin. But if we swap and do BA, oxygen is now on the origin. And so in this case, since the sites are symmetrically equivalent, it wasn't very interesting. But in this particular example that I have in the README, this is where it can really come into play. So for example, let's say you have a perovskite structure which has this label. And we're going to use, again, there's only 1 degree of freedom for this structure, but we want to basically see how the decoration changes between if we use the ABC decoration or the CBA. So in this case, again, we do AFLOW minus proto equals AB3C CP5 221 ACB. And then the parameters would be params equals 3.785. And I forgot to put the species, but so if we go back and we do .abc, so that specifies essentially the default decoration. And then we do CA, and remember alphabetical order. So even though we want calcium, titanium, oxygen, we need to do CaOTi. And that's because essentially the oxygen is has a composition, basically it's a 113, and oxygen has 3 essentially formula units. So you can see that it generated calcium at the origin, oxygen has 3, and titanium is essentially in the center of the unit cell. But maybe you wanted to switch which atom was in the center of the unit cell. So if you hit up to get to the previous command, the only thing you would change is now we want to swap basically the A and C sites, or species, I should say. So this would be CBA. And if we do this, now you can see calcium is in the origin and titanium, or sorry, excuse me, calcium is in the center of the unit cell and titanium is on the origin. So again, you would use this atom site decoration functionality to basically toggle or control between where you place these elements. And so there's a question, but the species still depend on the ordering in the Potcar, right? Yes, correct. The Potcar is basically, that's really where VASP reads the species information. But again, since we're generating just the postcards themselves, we're basically showing where the species are just for the geometry file itself. Actually, when you do the AFLOW in, again, that's really where, again, you need to make sure that the species information is correct, because when you generate the AFLOW in, it's going to grab information from the Potcar. And again, knowing where the species actually are is going to be important. But yes, the Potcar is going to have that species information. And there's another question, is it VASP5? You can create this in VASP5. Again, I think all you would need to do is AFLOW minus VASP5. And this will essentially give you the same. Okay, so there's a couple things. So yeah, as Dr. Esther said, AFLOW will generate the correct Potcars. That's correct, yes. So the other question was, okay, so you're asking if the command to get the elements written. Okay, so yes, to get the elements written, you would do, yeah, so you would do the VASP5 like this. Otherwise, okay, I see, yep. So yeah, you may need to pipe it to get the VASP5. But otherwise, if you don't do VASP5 by default for VASP4, if you generate these structures with AFLOW, they'll put them on the side here, the species here. VASP doesn't really read these. This is essentially a comment, but as a user, you would at least know how these are decorated. But then again, as was brought up by Alvin, yeah, this is going to be basically indicated in the Potcar. So yeah, great questions though. Yeah, these are good questions. Okay, so continuing with the example. So let me go ahead and go to the next subdirectory. So that's how you can control which atoms are decorated on particular sites. But now I wanted to mention the Svigard's or automatic volume scaling. So again, we saw this in session 1, sometimes when we would specify parameters or params equals -1. And again, this does, oh, sorry. Yes, there was a question about vacancies. Thank you. Is it possible to decorate in presence of a vacuum? In general, I think that might actually be, that might be closer to the slab command. So for example, I think we mentioned the slab functionality. So that's how you would introduce vacuum. So you could do kind of like a surface type calculation. As for vacancies, in general, with the prototype command, we typically don't specify vacancies because I guess we wouldn't know what to call them. I guess by hand, you could basically decorate with a fictitious atom, but I think otherwise we don't explicitly handle vacancies in this way. But I'll say that in the partial occupation module, when we're talking about basically for particular sites, you can decorate different species on these sites. You can also essentially decorate with vacancies. And so maybe the vacancies question will be more appropriately answered in the partial occupation module. So again, I believe that's day 3 or day 4. And you can actually, we may actually discuss how you can basically have partially occupied sites, and that can also include vacancies. Okay, so it looks like the terminal's a little small. Sorry about that. Let me go ahead and increase the font size. And I'll just do full screen. Hopefully that's a little better. Yeah, hopefully that's better. I'll try to kind of toggle back and forth so I don't need to reduce the size. But okay, so yeah, great questions though overall. So the next part was the automatic volume scaling. Excellent, okay. So for example, let's say you have, again, our favorite example, the rock salt structure, and you want to decorate it with magnesium and oxygen. And if we want to scale the cell size based on the atoms that are decorated in there, we can use this -1 parameter. And this uses the Vacancy's type scaling law that I mentioned before. So basically it takes into account the size of the elements, and basically it counts the number of elements of each type, and it scales the volume accordingly. So for example, again, we use our favorite structure, AFLOW -- Proto equals ABCF8 225 AB. And then just for consistency, we're going to use the atom site decoration. We're going to do MG and O. And then -- params equals -1. So what this does is you'll notice that this is kind of a standard 0 and 0.5 and 0.5 for the lattice vectors. But you'll notice, if you're familiar with how VASP treats scaling and volumes, if this is a positive number above the lattice vectors, it's a scaling. But if it's a negative number, it's the volume of the unit cell. And so in this case, basically, this is how we can control the size of the cell. So that's for magnesium and oxygen. But let's say instead, if we hit the up arrow, and instead we decorate with chlorine and sodium, again, we're going to have a similar geometry file, but the only difference is the volume of the cell changed. And that's because typically chlorine's a pretty large atom, and so we would expect that the volume would increase in comparison. And so what's nice about this method is, again, if we're trying to do things high throughput, we want to have a reasonable estimate of what the cell size is. And a good way to estimate that is based on the size of the elements. And so this is essentially a way that we can automate that process to have a close guess of what we think the volume would relax to. Again, we still need to do a relaxation to check, but this would be a good initial guess. Okay. So the next part is we'll go into subdirectory 4. And in this case, I wanted to highlight that we have enumerated parameter sets. So we've kind of taken for granted that the examples so far haven't had a lot of degrees of freedom. But in general, especially as you get to lower symmetry structures, there's going to be a lot of parameters that you need to specify. So for example, for an orthorhombic structure, this chalcostobite structure, you basically need to specify all of these degrees of freedom. So I'm just going to go ahead and copy this. Oh. Copying may be a little difficult in the VM, so I'm just going to do the explicit copy paste. Hopefully it's okay to paste. Okay, so yes, and so it generated this structure successfully, but maybe you don't always want to have to type out these parameters, especially since you want to use the default parameters and you don't want to type them out every time. So we've actually enumerated them. So instead of typing all of this, we basically come up with, excuse me, a lookup table in AFLOW. And basically, if you put this suffix -001, we have a lookup table, and basically it'll grab the degrees of freedom that correspond to that suffix. So instead, let me go ahead and type it out. So in the README, we have the two versions specifying the parameters explicitly or using this enumeration. So we do AFLOW -- proto equals, so you do the label first. (62C 2CC). Then immediately after the label, you do the enumeration. So in this case, it's 001. And then site decoration, CUS. And you'll notice we didn't have the params flag, and that's because basically we're using this enumeration. And if you were to compare the geometry files, they would be exactly the same. And so your question might be, well, what parameter sets are available? Because there could be -0, 001, 002, and what do they correspond to? So if you do have a label, let's say, for instance, this label here. So you can see what parameter sets are available by doing essentially typing the command. And in this case, this one has quite a few, so I want to use this as an example. So this is proto equals AB2 OP6 OP6 58 A score G. So if you just type the label, no degrees of freedom, you'll get an error, and it's kind of hard to see since we've zoomed in so much. So, but basically what it's showing is this here. So it's basically saying there's an error. Actually, there's a typo since I typed it out, but there's actually 5 preset parameter sets. And basically it's telling you that this is the enumeration and these are the degrees of freedom. And so basically this can tell you what the degrees of freedom correspond to each suffix or enumeration. Okay, so basically that's how you can create these structures via the command line. We already did see, but we'll just, for good measure, so we were just generating the geometry files, but the same syntax applies to AFLOW Proto as we saw. So we won't regenerate all of these, but essentially, hopefully now these make a little bit more sense. So basically, the only difference between generating the geometry file and the AFLOW in is you add this minus minus AFLOW underscore proto. And so you follow the same syntax. If there's degrees of freedom, as we saw, you add them, but the only thing that's different is this AFLOW, and this will generate an AFLOW in for the particular structure. So I won't go through exercises for this because we've already done this quite a few times in session 1. But as a refresher, either during the break or on your own time, I believe there's some discussion in the README as well. Well, maybe for good measure, just to do it while we're here. So we'll do AFLOW minus minus AFLOW underscore proto equals ABCF8 225 AB is the default decoration, MGO. Again, especially for AFLOW ins, I highly recommend, unless you're doing a particular cell size that you know of, I would recommend doing params equals -1, especially if you're going to be changing the species. And then you would see that it generates this AFLOW data, MGO, and ABC. So again, this subdirectory structure. And then here's the AFLOW in. And it corresponds to this structure. So it looks like there's a question in the chat or a comment in the chat. I was trying the Ames output. It seems the lattice vector does not change even with changing the species. It's a good question. It should, unless there's something going wrong. So essentially it would be AFLOW minus minus, so just proto in this case, equals ABCF8 225 AB so this should work. So Ames, and then if you do CL, it does change for me. So if you change the species, you'll notice that the lattice vectors do change based on magnesium and oxygen and chlorine and sodium. Are you still seeing that error, or? I guess let me know in the chat. Yeah, let me go ahead. Yeah, if you want, you can put the command in the chat. I'm going to put my command in the chat as well. So again, just as a reminder, it would be something like this. So that should be 1. And then if you just want to do MG and O, it would be something like this. So, and you should see that the lattice vectors will change. But yeah, feel free to post the exact command that you were running and we can help you debug. But in general, they should change with the species. Okay, let me hide that. Okay, so that's how we generate the AFLOW ins. And so there are a lot of different prototypes you can either check online. So you can go to aflow.org prototype encyclopedia, as I showed before, or you can type AFLOW minus minus protos. And actually this will give you a full table of everything that you can generate in AFLOW. So for example, if you do AFLOW minus minus protos And instead of just running the command, I'm going to pipe it to a file. So this is going to be protos.txt. All right, so this is the contents. And so there's some information about AFLOW, some important citations, but then below this, these are all of the prototypes that you can generate. So you'll notice that some of them are these hard-coded that I mentioned before. So typically the ones at the beginning are these hard-coded enumerated. So you could do proto equals 1, proto equals 20, and basically here's some information about the Pearson symbol, symmetry, any common name it might have, some notes. And then if you want the ones that are basically the newer prototypes that have this underscore scheme and have a little bit more degrees of freedom, those are shown here. And you'll notice that it gives you the label, the enumeration, and it also tells you basically right here, it tells you the site decorations that are equivalent. So if you see that the decoration is in brackets, that means that AB and BA decorations are symmetrically or structurally distinct. But you'll see something like this, for instance, where there's only AB, and this tells us that AB and BA are equivalent. And so I'll discuss that in a little more detail when we introduce the Extil Finder module, which determines similarity between crystal structures, and it can also determine similarity between prototype decorations. So we'll see that in a bit more detail. But essentially, these are all the prototypes you can generate. There's actually more than that are online, and that's just because we are finding more prototypes, and we're finding prototypes at a faster rate than we can put them online. And so a more comprehensive list is given with AFLOW ---- protos. All right, so with that, the last couple things that I wanted to mention was the AFLOW prototypes label. So for instance, if you wanted to find a particular prototype label that has 2 species, a stoichiometry ratio of 1:2, and space group 225, you can do that. So you can do AFLOW ---- prototype labels. And then you can add n species equals 2. Stoichiometry ratio of 1:2. Stoichiometry equals 1, 2. And this will search for 1, 2, and 2, 1, so the permutations as well. And then space group 225. And you'll get a comma separated list of all of the prototypes that have this, these characterizations. And so I've highlighted a lot of functionality. And again, if you need a refresher or you want to know what other options are available, you can type AFLOW ---- readme equals prototypes. So AFLOW ---- readme equals prototypes. And again, we're going to pipe this to the command. Or type this to a file. And here's some information, so some citation information. Again, the general syntax of how you would generate the structure. Again, these prototype aliases or enumerations. And again, more information about the syntax and what it means. And again, some additional options. So if you'd like to refer to that, that's available as well. Okay, so with that, okay, so it looks like you gave the commands. Actually, what I'll do is I'll go ahead and look at that maybe during the exercises. In general, this should work, but it could be an issue that in general, AFLOW is expecting different species. And so the fact that you're decorating with different ones, I didn't think that would be an issue, but let me double check during the break, or excuse me, the exercises, and I'll see what's going on there. In general, I would believe that would work, but I'll check in a second. So I guess what we can do is we can go ahead and get ready for the breakout rooms. I don't know if we still have the rooms set up, but in the meantime, if somebody wants to get that started, but basically I was going to highlight the exercises. So the first one is an online exercise. And basically I wanted you to search for these structures, and I would recommend using the search functionality. So essentially just going to this bar here, and you can basically type in the common name here and it should pop up. And basically, what are the AFLOW labels of these structures, and kind of see if they make sense. So you can divvy that up between members of your group, or you can all do them. The next is to generate structures for a particular prototype. So this is this particular prototype label, and you're going to pick any value of A that you'd like, but then you're going to change the C over A value, and you're going to create essentially, I think, 7 structures. So the first structure will be, let's say, lattice parameter A equals -1, and then C over A 0.5. You'll generate that structure and save it. Then you'll generate this next one, -1 for A, and then 0.612 for C over A, and save that structure. And you'll create all the structures and then determine what the space group of these structures are, and see if they change. The next one is to control the atom site decoration. So essentially you'll create a structure, and then basically I want you to decorate it with 4 different species, and then basically use this .abcd or .bca functionality to basically decorate these onto different Wyckoff sites. And as a note, basically I've told you what the corresponding Wyckoff position is for A, B, C, and D. And then finally, generate a Heusler structure, determine the space group, Wyckoff positions, and Pearson symbol with the space group functionality that we saw in the previous section, or symmetry functionality we saw. And then I want you to guess or kind of construct on your own what the AFLOW prototype label would be. And again, depending on what the elements you choose, they may be permutated slightly in comparison to maybe your colleagues, but in general, the overall label should look similar. So with that, I'll go ahead and stop sharing. And then if we can go ahead and go into our breakout rooms, and maybe we can spend, I'd say about, let's spend maybe 25 minutes. And if people finish early, we can come back, but let's spend about 25 minutes. Okay, so if there are any questions outright, please feel free to post in the chat. Otherwise, I'll quickly go through the exercises. But otherwise, let me go ahead and, actually, the first thing that I wanted to mention is I did look at, I think it was Alvin, if you're here, I looked at your particular structure. And I guess the first thing is that it looks like you're missing the third field. So for example, give me 1 second, I copied the command, but essentially in comparison to the command that you had, you were missing this last C here. So it's a ternary, so you basically need these 3 Wyckoff positions there. And so if you do that, and then yes, the other thing is that alphabetical order does matter. And so if you were to do this, again, I guess I can copy it into the terminal so everyone can see. But if I go ahead and copy this into the terminal, so we don't need to specify the site decoration here. You can do it that way, but you should see that, okay, so in this case, remember that it's 5.22. And then if you wanted to do all copper like you did in your example, and now it's 5.02. So there is a shift. It looks like, again, having things in alphabetical order for AFLOW is very important, especially when it comes to this Vegard scaling law, as we see as well. So hopefully that helps, and hopefully that's clear for everyone. All right, so for the exercises, the first one I won't go through, but essentially this one was just to kind of explore the website. And so just to kind of navigate there. But this next exercise was basically, I wanted you to generate 7 structures and analyze the space group symmetry. So I'll do that quickly, and then I'll explain essentially why I wanted you to do this exercise. So again, it's AFLOW Proto equals A HR1 166A. And just for consistency, .A for the site decoration, I'm going to use iron, and then params equals, so the first lattice parameter A, I said you could do anything. And then the second one, I wanted you to do 0.5, and then all of the other ones separately. So, but first I wanted you to analyze the space group. So we're going to type it to the space group command. And if you do this, as expected, you get space group 166. But if you change it to the C over A ratio to 0.612, now you get space group 229. And so it's actually different than what I had said before. I had said that if you basically change the degrees of freedom, you'll be in keeping of that symmetry consistent with the label. And so you'll notice that, again, if you continue to change the degrees of freedom, I'll just do a couple more that are interesting. So for example, 2.45, that one is actually space group 225. So I'll essentially amend my statement that I said before, that basically if you tune these degrees of freedom, you'll exhibit the symmetry of the label, or you may fall into a higher symmetry class. You can't fall into a lower symmetry class because we're not allowing you essentially to break degrees of freedom, but you can actually fall into a higher symmetry class. And so that's kind of the revised statement. And it's actually a nice way of, this is a nice example because you can actually see that if you stretch, your cell along the C over A, or the C axis, then you can basically kind of deform your cell and fall into a higher symmetry class. And so you can see the relationship, for instance, between this rhombohedral system and then these body-centered and face-centered representations or systems. So that was the goal there. This next exercise was basically to kind of hone in your skills for basically decorating elements onto different sites. And this one was a little tricky because there's a lot of A's and B's and C's, but essentially what I wanted you to do here was create the quaternary Heusler. And then basically I give you the label. So we'll just kind of type that out really quick. 216 C B B A params equals -1. All right, now I'll go back. And I know that I want silver, copper, iron, colon delimited, iron, and manganese. And so now really the only thing we're going to be changing is the site decoration. And so in this case, for the first structure, I wanted basically silver to be on the B site. And so you kind of need to keep track, but basically the B site corresponds to the C position here. So you put C. Then for the A position, basically the next species, I want an A, which corresponds to D in the label. Oh. We ran the command early and it broke. So D. Then the next site is C, which corresponds to the A site in the label. And then last but not least, there's B. And so if you do this, basically, so you can check, basically I told you what positions correspond to each Wyckoff label. So A is 000, and that's where copper is, as we wanted. 555 is silver, which is where we wanted a site B, and so on and so forth. So that's just an example of how you can control that. And then the last exercise was I gave you the prototype label for the Heusler structure without any degrees of freedom needing to be specified. So we would do AFLOW -- proto equals T0001.A2BC. No degrees of freedom necessary. And you can generate the structure. You could put any elements you want. Forgot to add that. So I'm going to put NNPDPT. And there we go. And again, this automatically does the Vigard scaling as well. Then I wanted you to analyze the space group. You can use AFLOW-SG. Then I wanted you to analyze the Pearson symbol. CF16. And then I wanted you to analyze the Wyckoff positions. And then based on this information, I wanted you to determine what the AFLOW prototype label with the underscores would be. So you can easily go back to how we basically came up with the label or the definition of the label here. So the first is the reduced stoichiometry. So basically there are two MNs, so that's A2 and then BC. Then we have the Pearson symbol, which we calculated, CF16, space group 225. And then we had for Wyckoff positions for site A, it's C. Then for site B, it's A. And for site C, it's B. And that would be the label. And so actually in session 10, so on Friday, I'm actually going to show you how you can use AFLOW to automatically create this label. So now you know how to create the label. You'd have to do it by hand, but there's a command with AFLOW that basically you can take any geometry file and it'll automatically determine the label, but then also the degrees of freedom, which may not necessarily be as trivial. And so basically you can convert any geometry file into this prototype designation, and also you'll have access to which degrees of freedom are constant or not. And so with that, the other thing that I wanted to mention is I've shown you that basically there are certain prototypes that you can generate in AFLOW, but if you follow this syntax of generating the prototypes, you can generate any crystallographic structure. So even if we don't have it yet in the encyclopedia, as long as you follow the correct syntax, you can generate an arbitrary structure. And so basically we basically have a symbolic prototype generator. So as long as you follow the correct syntax, even if it doesn't exist in the encyclopedia itself, you can still generate the structure with AFLOW. And again, we'll see a little bit more of that on Friday, but I just kind of wanted to give you a quick flavor or a quick introduction that that's what we'll be doing on Friday. All right, so with that, I think we'll be able to end a little bit early, but the last thing that I wanted to mention is, again, I already mentioned this prototype command or this README. So basically, again, if you want more information on how to generate these prototypes with AFLOW, again, this will be really important when we're doing the future modules. So when we're doing the phonon calculations, when we're doing partial occupations, so disordered systems, a lot of these rely on generating these prototypes. And so again, if you have any more questions about this, feel free to post in the chat or email us, or you can look at these READMEs or these articles on how to generate these prototypes.